Good afternoon, everyone, and thank you very Good afternoon, everyone, and thank you very much for joining us today to this webinar on application of low power sensors according to the standard IEC 61869. My name is Oscar Pereira, and I work in ZIV in the commercial department. Well, today events is part of ZIV's 2025 training plan that includes free online sessions like this one. Also, as well, we organize paid in-person training sessions that we call ZIV University that we organize both in Bilbao and in Barcelona. In any case, every third and fourth Thursday of each month, we will be organizing free webinars like this one. In any case, all the information about our training offerings are available in our website. So you can check the same in visiting zivautomation.com. Well, today's session will last 30 minutes. So the first 20 minutes will be dedicated to the topic presentation, and the remaining 10 will be available for you for any question or clarification that you may need. Well, so at this point, please, I encourage you to click on the display button that you can find in your screen on the lower side, and select the full option, the full screen option, so you will have a better viewing experience. As well, you can use the chat feature to send us any question, so I will transmit the same to our expert today. So at this point, I am pleased to introduce you my colleague, Carlos Gil. He's the product manager of the sensors product line in ZIV. So, Carlos, are you there?
Yes, thank you. Thank you, Oscar.
Okay.
Hello, everyone. Thank you for joining today to this webinar. We are going to talk about the application of low power instrument transformers according to the new standard IEC 61869. This is an information that it was presented in a paper in the last PAC event. So, well, the presentation is divided according to this index. We are going to talk about what is low power instrument transformers, and then we will see what kind of implications in the design of LPAT and IED it have been done due to this new standard. So here you can see a diagram of the electrical grid. Okay, we have the stage of generation, transmission, distribution. Here, at least in Europe, due to the European directives, all the utility companies are focusing in the monitoring and supervising the distribution area. So this is a different task like fault detection, falling neutral, measurement of electrical parameters of the grid quality, device status, alarms, and this task has been possible if we use two key components, low power instrument transformers and IED, that this is the acronym of Intelligent Electronic Device. Both of them are framed now under one standard. It is the standard commented previously in the title 61869. Well, the low power instrument transformers, or also called sensors as historically, we call here in ZIV, have three main functions or roles. The first one is adapt the high primary voltage or current to values that can be managed or handled by the electronic device. The second one is give an electrical insulation for the devices connected to them, the detection and control devices or measurement. And finally, the most important is the measurement of the electrical parameters, voltage, current, phase shift, with a linearity in a range of temperature. The low power instrument transformers has a list of benefits against the conventional transformers or traditional transformers. The first one is the size, normally are smaller. The costs are cheaper. The linearity, we have more linearity in a range of temperature. We don't have saturation or hysteresis in terms of voltage dividers. And we can supply or use these low power instrument transformers in different shapes according to the application where they are going to be installed. We have two types. LPVT is the model for voltage measurement, and LPCT is the current transformer. Well, the new standard is an international standard that applies with the technical requirements that the sensors and IED has to comply. Here, the standard is divided in different parts. Here the list is an example or an extraction these applications. The first one, the piece 1 is the general requirements. Piece 6 is integrated now in the number 1, and we have 10 and 11 that these are the parts that applies to the current and sensor low power transformers. And the 13th part is the SAMU. It is the acronym of standalone merging unit that applies more close to IED. And finally, it is in development part 22 that it is applies to low power instrument transformers that will be integrated in other electrical devices like cables, connectors, bushings, or insulators. Well, this standard, the requirements specified in the standard has different implication on the sensor design. The first one is regarding to connectors and wiring. The standard describes or recommended the use of two types of connectors. RJ45, this is the connector that normally we use to connect to Ethernet network with our laptop. We have also for outdoor application M12. It is a multi-pin connector for threaded for outdoor application. And in case that we have a signal higher than 10 volts, we normally, it is recommended to use screw terminals. The pinout of the connector is completely defined in the standard. Here we can see an example of RJ45 where we can see that it is reserved the pins for low voltage transformer and for low power current transformer also. And in case that we are going to use an active sensor, we have 2 pins, 4 and 5 for the power supply. The second one is the wiring. The cable must be considered as part of the LPIT, and for connections longer than 10 meters, the use of coaxial cables or shielded cables is recommended. Well, in terms of accuracy, the standard specifies what are the classes of accuracy. Depends on the application. For measurement, we have, in case of the low power current transformer, 7 classes, and for protection 3. And in low power voltage transformer, we have a third extra class that it is multi-purpose, this is a class of accuracy that try to integrate in one class the requirements of protection and measurement. At following, we can see an example of what is the difference between a measurement device or multipurpose device. Sorry, because the table is in Spanish, but the data is easy to understand. We are comparing 0.5 accuracy class. Well, you can see in the left table that the range that we have to comply is from 80% of the primary voltage to 100% multiplied by a voltage factor. And in case of multipurpose, we have to comply a wider range because we have to comply from 2% of the primary voltage to 100 multiplied by voltage factor. So it is more difficult to design a sensor for multipurpose than for measurement. Regarding to burden and secondary voltage, the standard specifies the impedance that the electronic device has to have as an input, because we are talking about passive devices, so a change in the impedance could modify the ratio of the sensor, and it is also specified in the or described in the standard the secondary voltage. As you can see, in the case of current transformer, it is not as always for conventional transformer that normally we have current in the secondary signal. Here also we have a voltage and lower value of the signals. We are talking about millivolts instead of volts in the case of voltage transformer. And we have to comply with this accuracy class when we have a variation of the resistive load plus minus 5% and in the capacitance 100%. Here we can see a diagram when we can see a resistive divider from the left to the right, in the middle a capacitive divider, and the third one is the real one, because always we have, in the case of resistive divider, parasitic capacitance in parallel, and in case of capacitive divider we have resistive losses. Well, another thing that we have to take into account in the sensors design is that now in the standard it is required a frequency response, because as we told in the previous slide, we have to check the quality of the grid, and for that we have to have control about what is the response of these sensors, that they are doing measurements of the voltage and current, and depends on the application. We have a wider range that we have to comply in terms of frequency. Here we can see an example comparative of capacitive divider and resistive divider. In the graphics of the left is the ratio error, and the right is the phase shift error. So we can see that both of them are inside the limits of the table. Well, once we already clarified what are the terms that affects to the sensor, we are going to get into the IEDs. Well, the part that affect more, or it is more close to IED, is the part 13. Normally, conventional transformers deliver higher values to the protective or measurement devices. Not is the case of the low power instrument transformers, that, as you can see in the previous slide, they give a lower value. So we have to adapt the input stages of our electronic to make a correct measurement. So the LPDT inputs of the IED device normally are referenced to ground, In the case of LPCT, normally are differential inputs because we have a problem with the noise. The LPVT ground and IED ground might or might not connected to each other. And in general, there is a galvanic insulation between the input ground and the internal ground. We have an extra case that in terms according of LPCTs based on Rogowski coils, we have to take into account that the signal from Rogowski coils, it is a derivative from the primary current. So to have correct data, we have to make an integration of this signal, and this integration could be done by hardware or by software. Well, another important thing to take into account is the IED can work or act as protection, fault detector, or RTU. So in that case, we have to know that the input of this device has to comply with two classes, protection and measurement, and it is relevant because the dynamic range is very wide. So here we can see the first table, a frequency response for measurement class, and at the bottom we can see the table for protection. For protection, we have to use to inject a high frequency signal that is called also COCO. It is close, open, close, open. It's an exponential signal where we can see the instantaneous error of our inputs. In the next slide, we can see the response of ZIB-IED in terms of measurement in the left, that complies with class 0.2, and in the right, in the protection test with the COCO cycle test that complies with 2 TPM. Well, I would like to show you a real case that this is a rural line with 15 kVs. It is a configuration grid of insulated neutral. We use here a combined active sensor where we can measure current and voltage in the same piece, and the IED is the RGDM. Here on the left, we see two graphics. On the top, the voltage, and on the bottom, the currents. We see that at one moment, the phase A has a fault, and the two healthier phases increase the value of voltage until a moment that the IED works. In the bottom, we can see capacity disturbance according to the configuration of the grid. Finally, let me show you a little bit 3 examples of our portfolio that complies with this new standard. The first one, it is our sensor for GIS. It is a sensor for connection indoors in a switchgear of 24 kVs for interface C of bushing. The accuracy class is 0.5P. It's multi-purpose sensor, and the improvements to the previous model are according based on the new standard. It is based in one piece and has some better accuracy class. The second example is regarding to LPCT sensor. It is a sensor for GIS also. It is based on toroidal core. The accuracy class of this sensor is 0.2S in terms of measurement and 5P20 for protection. And it is based also in one piece and with a RJ45 connector. And the last one is an example of IED. It is a device that has many main functions as current and voltage protection, automatic fault detection. Well, you can see the list here in the slide, but I would like to focus in the current input characteristics and the voltage input characteristics, where you can see that the input impedance is according to the standard. The secondary values are also according to the standard, and the accuracy class that this input has. And finally, I would like to conclude with these 4 conclusions. The first one is the LPATs proved to be an excellent alternative to conventional or traditional transformers due to its adaptability to the application or the installation environment. The IED will be an equipment that unifies in a single device the task of protection, measurement, and control. This new standard will promote the interconnection or interoperability with the different manufacturers. And finally, this standard is constantly evolving to adapt to the customer requirements. So thank you, everyone. And now feel free, if you have any question to ask me, I am here available to attend you.
Okay, thank you, Carlos, for your explanations. Well, I am checking now the chat, but for the time being, I think we didn't receive any questions so far. So please, if any of you following the webinar has any question or requires further clarifications, please feel free to drop your question there. In the meantime, well, as I told you at the beginning, I am working in the sales department. Quite often I receive questions from customers. So Carlos, perhaps the most frequent question that I get from the customers is related to the current sensors, to the LPCT. And usually they ask me what kind of LPCT can we find in the market, or in our case ZIB can offer, regarding specifically to the current transformers.
Okay. Well, the 2 types that we can use as LPCT sensors, we have 2 types. The first one is LPCT proportional. The LPCT proportional is based of magnetic core or toroid core, where the secondary signal is proportional to the ratio of the winding of the core. And the second one, it has been commented during the presentation, is the Rogowski coil, or also known as derivative sensor. This name comes because the secondary signal, it is a derivative of the primary current. So it is needed an extra element that could be done by hardware in the proper sensor or in the electronic device, or maybe can be done by software. It is the 2 types that we can use.
Okay, thank you. And so, following with that, you as our project manager for this field, which is the roadmap that we are forecasting in ZIB for the coming months or even years? Which are our plans in terms of developments?
Now we are working in develop an outdoor sensor for 24 kbs line. This sensor will be based on bushing body to be connected in the symmetrical T-connector for outdoor application. Also, we are working in different sensors, current sensors, for different primary current ratio. And regarding to IED, here in the Spanish market, We are at the final stage of the new RTU that improve the accuracy class in the inputs and different functions that the smart RTU.
I see. Okay. And finally, perhaps for those customers that still are evaluating the possible migration or not to this technology, to this kind of sensors, that it's normal that they could feel afraid of this. Which are the biggest challenges that you would see in this replacement operations between the conventional instrument transformers and these low power instrument transformers? What is your message, let's say, to encourage the customers to go for it, at least in a step-by-step basis? What do you think?
Well, the principal challenge of the change of conventional transformer to LPIT is the devices that they are connecting now to the conventional transformers are prepared to manage high level values of voltage from the signals from the conventional transformer than LPIT give lower values. In terms of that, there is some accessories to adapt the signal from LPITs to the all school electronic devices. So this, from my point of view, is not a problem. And the second problem maybe is to again has to homologate or validate the new junction, but in the close future they are going to do the step forward to the new technology as in other worlds. We have to move forward because the technology are better than the previous one.
Yeah. Okay, I see. Thank you, Carlos.
Thank you.
Well, we are about to complete the time we have allocated for this webinar. So I don't know if there is any other question. If not, otherwise, I want to take this opportunity. Well, first of all, to thank you, all of you, for your presence and active participation in this webinar. Also, 2 or 3 messages before we finish. One is that I remind you that on the next March the 20th, that will be the third Thursday of next month, we will host another webinar. In that case, it will be related to the RTDS software and the application on substation automation systems. So I'm sure it will be also of great interest for many of you. And also I want to inform you that we have just created a new webinar for that you can assist related to the application of distance protections. So I will give you the link now via the chat, so you can, if it's of your interest, you can register to assist to this, also to this new webinar on distance protection. So here you are the link for registration. Okay. And finally, also very important is that after we finish this webinar, automatically you will get an email with this all these presentations and discussions. So any of you can check this content offline. Okay. So from my side and also from our side in general, once again, thank you very much for joining us today. and we look forward to seeing you again at the next seminar. Good afternoon and thank you.
Thank you.